So when we studied the span of a set of vectors, v1 through vn, we were interested in determining how to answer questions of existence. So given a set of vectors, v1 down to vn, that are m-dimensional, for which m-dimensional vectors b does there exist an n-dimensional vector x, such that the matrix, whose columns are v1 through vn, multiplied by x is equal to b. So in this section, we turn our attention to the question of uniqueness. So given an element, b, in the span of these vectors, v1 through vn, when is the vector x above that satisfies this equation unique? So let's start off with an example. So we have three vectors, u with entries 0, minus 1, 2, v with entries 3, 1, minus 1, and w with entries 3, 0, 1. So we can use Sage to compute the following row equivalents. So the last row in our reduced row echelon form tells us that the span of u, v, and w is a plane, and it's cut out by the equation a minus 6b minus 3c is equal to 0. The reduced row echelon form for our matrix also tells us exactly how to write any vector that lies in this plane in terms of the vectors u, v, and w. So in particular, we see that the representation of any vector in the span of u, v, and w is not unique. We can choose any value that we like for the free variable z. In particular, if we break this vector into two vectors, we can actually see that it forms an entire line of solutions. However, we can make one interesting choice here for the variable z. If we let z be 0, then we get the following. Our observation here is by simply taking z to be 0, we've actually removed any dependence on the vector w for any element of the span. And in fact, we could see this explicitly by removing the third column from our augmented matrix. Using the exact same row operations, we'll get the following row equivalence. And this row equivalence tells us that the span of the two vectors u and v is also the plane cut out by the equation a minus 6b minus 3c. And what's more, we can see from this reduced row echelon form that the representation of any vector as a linear combination of u and v is necessarily unique. Now, if we return back to thinking about the vector w, we can actually think about w as being an element of the span of u and v. To do this, we simply need to think about the reduced row echelon form of our coefficient matrix. If we shift our perspective just slightly by thinking about each of these three matrices as augmented matrices, then we can see that w, in fact, can be expressed as a linear combination of u and v, where the weights are simply 1 and 1. So this relationship between these vectors is actually important enough to warrant its own name. So we say the vectors v1, v2, down to vn are linearly dependent if any one of these vectors can be expressed as a linear combination of the others. Note that the vectors v1 through vn are linearly dependent if and only if any one of the vectors lies in the span of the others. If the vectors are not linearly dependent, then we say they are linearly independent. This is a really important concept, and it's going to be one that we spend a fair bit of time exploring.